Neural networks are everywhere, from the recommendations on your favorite streaming platform to the voice assistant in your pocket. But how do they actually work? Let's peel back the layers of this mysterious term that often gets tossed around in conversations about AI and machine learning. At their core, neural networks are inspired by the human brain, but they're not carbon copies. Think of them as mathematical models made up of layers of interconnected nodes, also called neurons. Each of these neurons receives input, processes it, and passes it along to the next layer. To understand how this works, let's start simple, with a single neuron. A basic artificial neuron receives inputs, numbers, each with a weight attached. The neuron adds them up, applies a bias, another number, and then passes the result through an activation function. This function determines whether the neuron fires or not, meaning whether the information continues traveling through the network. Now imagine a whole layer of these neurons. Each one is connected to every input and to every neuron in the next layer. This forms what we call a fully connected network. A typical neural network consists of three types of layers. One input layer where the raw data enters, like pixels of an image. Two hidden layers, the intermediate layers that process the data and extract features. Three, output layer where the final prediction or decision is made. But how does the network learn? Learning happens through a process called backpropagation. Here's how it works. The network makes a prediction. It compares the prediction to the actual answer, known as the ground truth. It calculates the error using a loss function. Then, it adjusts the weights and biases of the neurons to reduce that error. This adjustment is done using an algorithm called gradient descent, which gradually tweaks the weights in the direction that reduces the error the most. Here's an analogy. Imagine trying to find the lowest point in a foggy valley. You can't see far, but you can feel the slope under your feet, so you keep stepping downhill until you can't go any lower. That's gradient descent. Each cycle of prediction and correction is called an epoch, and the network usually needs thousands of these to learn effectively. But not all neural networks are created equal. The simplest ones are called feed-forward neural networks, where data flows in one direction, from input to output. These are good for tasks like classification and regression. Then you have convolutional neural networks, CNNs, which are used in image recognition. CNNs add special layers that detect edges, shapes, and patterns in images. That's how your phone recognizes your face, or how self-driving cars detect pedestrians. There are also recurrent neural networks, RNNs, which are used for time series data like speech, music, or stock prices. RNNs have loops that allow them to remember previous inputs, like remembering the context in a sentence. More recently, architectures like transformers have revolutionized the field. Transformers can process sequences in parallel rather than step by step, making them faster and more powerful. They're behind models like ChatGPT, BERT, and many other modern AI systems. So why are neural networks so powerful? It's because they can approximate complex functions. Given enough data and layers, a neural network can learn to model almost any relationship between input and output, whether it's recognizing handwriting or translating languages. But with great power comes great responsibility. Neural networks are also black boxes. meaning it's hard to understand exactly how they reach their conclusions. This raises concerns in high-stakes areas like medicine or criminal justice. That's why researchers are working on explainable AI, tools that help us understand what the network is doing under the hood. Training neural networks also requires massive amounts of data and computing power. It's why big tech companies with powerful GPUs and access to giant data sets often dominate the AI landscape. Still, open-source frameworks like TensorFlow and PyTorch have made it easier for students, researchers, and hobbyists to build and experiment with neural networks. And neural networks aren't just for researchers. They're helping diagnose diseases, improve the weather forecast, generate art and music, and even compose poetry. Their impact spans every industry, from finance to education to healthcare. To recap, neural networks are layered structures of artificial neurons. They learn by adjusting weights through backpropagation. Different architectures are used for different tasks: CNNs for images, RNNs for sequences, transformers for language. They're powerful, but sometimes hard to interpret. And they're transforming the world around us. Understanding how neural networks work isn't just for engineers anymore. In a world increasingly shaped by AI, knowing what's happening beneath the surface is a form of digital literacy. Because once you understand how a neural network sees the world, you begin to see the world differently too. Let's rewind for a moment and ask, where did all of this begin? The concept of neural networks dates back to the 1940s. Psychologists Warren McCulloch and Walter Pitts created a simple model of a neuron based on binary thresholds. But it wasn't until the 1980s, with the development of backpropagation, that neural networks began to gain traction. Fast forward to the 2010s, and we hit the deep learning boom. Why? Because three things came together: huge datasets, better hardware like GPUs, and smarter algorithms. The breakthrough came when a team at the University of Toronto used a deep convolutional neural network called AlexNet to win the ImageNet competition in 2012. Their model crushed the competition and sparked a wave of interest across tech industries. Since then, neural networks have gotten deeper, some with hundreds of layers and more specialized. Take AlphaGo, for example. It used deep neural networks to defeat the world champion in the complex board game Go. This wasn't just a milestone for AI, it was a cultural moment. Go had been considered a game too complex for machines to master due to its near-infinite number of possible moves. Or consider how neural networks power language translation. Tools like Google Translate now use transformer-based models to convert sentences between languages, and they get better the more you use them. These models don't just swap words, they understand context, tone, and even slang. In medicine, neural networks help radiologists detect tumors in scans with accuracy that sometimes surpasses human experts. In agriculture, they help farmers predict crop yields based on satellite eye imagery. In music, neural networks can create entirely new compositions in the style of Mozart, the Beatles, or EDM. But perhaps the most accessible use of neural networks is in recommendation systems. Think Netflix suggesting a movie you love, or YouTube surfacing the perfect video at 2 a.m. These systems learn and adapt to your preferences. Still, building neural networks isn't all magic. Training them is computationally expensive. Training large models can take hours or days. They're also prone to overfitting, when a model learns the training data too well and performs poorly on new unseen data. To counter this, techniques like dropout, regularization, and early stopping are used. There's also the issue of bias. Neural networks learn from data, and if that data reflects social biases, so will the model. That's why ethics in AI has become a critical field, pushing for fairness, transparency, and accountability. Another fascinating development is transfer learning, where a neural network trained on one task can be adapted to a different but related task. For instance, a model trained on millions of general images can be fine-tuned to detect specific types of tumors with a smaller dataset. And then there's unsupervised learning, where networks try to find patterns in data without labeled examples. This is the frontier of AI research, enabling models to learn more like humans by observation and exploration. The future? Neural networks that not only learn, but learn how to learn. This is called meta-learning, or learning to learn. It's a step toward general intelligence, systems that can adapt to new tasks quickly with minimal data. In education, neural networks are already being used to personalize learning experience. In finance, they analyze market trends and flag suspicious transactions. In transportation, they optimize traffic patterns and power self-driving systems. Even creative industries are adopting neural networks. Fashion brands use them to predict styles. Architects generate conceptual building layouts. Writers co-author novels with AI tools trained on literary classics. So, how do you get started if you want to build a neural network? First, understand the math, linear algebra, calculus, and probability. Then, start small. Use platforms like Keras or PyTorch. Build a basic model to recognize handwritten digits using the MNIST dataset. Once you understand the workflow, data in, prediction out, loss calculated, weights updated, the mystery begins to fade. From there, you can explore more advanced topics, CNNs for vision, LSTMs for sequences, GANs for generative tasks, and transformers for natural language. Neural networks are powerful tools. Tools we shape and control. They don't think like us, but they help us think in new ways. And maybe that's their greatest gift, not just performing tasks we used to do manually, but showing us new ways to perceive, process, and predict the world. In a way, studying neural networks is like looking into a digital mirror. As we teach them, we learn about ourselves.